Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to help you out with numbers 17, 18, and 19 in your Unit 3 homework. So let's see, a lawnmower blade which has a 2.4 meter diameter, rotating at 2500 RPM. Something to notice here, it doesn't say anything about this changing. So I think from the wording of the problem that we can assume this is constant. So finding the angular speed in radians per second, just start with this 2500 RPM, and I suggest you write it like this, 2500 revolution over minutes, because really that's how that unit should be written. And then this is just a unit conversion, so you're going to multiply by a some sort of conversion, and you're going to want to have radians up top and revolutions on the bottom. I'm not going to give you the conversion factor. And then what you'll do is you'll multiply by another conversion factor to convert the minutes to seconds. So that should be enough to get that one done. So part B, where it says find the speed in feet per second of a point on the tip of the blade. So the blade, if we did a quick little sketch here, the tip of the blade is going in a circle. And the distance it travels every time it goes around is 1 circumference, which is equal to 2 pi times the radius. So the radius you can get from this. Keep in mind that the 2.4 feet is the diameter, not the radius. Now, there's a couple ways to work this, but I would suggest this. All right, speed, which is the magnitude of your velocity, is distance over time. Start by writing this formula out. All right, now, because this is a constant speed problem, we can actually choose the time to be anything we want. So if I were working this, I would choose a time frame of 60 seconds. And the reason for doing that is because we know it's rotating 2500 revolution per minute. If we choose a 60-second time frame, we will know that it has went around 2500 times. So the total distance traveled would then be 2500 times the circumference, and then divide by the time. That should get you through that problem. All right, scrolling down. Once you know the speed, right, and again, remember your magnitude of v, that's your speed, is distance over time. You can then take your known speed and our time here and get a distance. And part D is virtually the same thing, just a different unknown, and watching your units carefully. That's probably enough on 17. Okay, 18 is about my chicken plucker at home. So what I have is, it's a machine. It's about the size of a small washing machine. I'll take a picture of it and maybe put this in the homework. And it's got this round drum part to it, if you will. And here's where the chickens go. They go in here, and it's got these little rubber fingers, and it rotates around, and it takes the feathers off of the chickens, believe it or not. So let's see. As we read this problem, person turns on the chicken plucker, and the tube rotates from rest to 300 RPM in 2 seconds. I'm just guesstimating values here when I made this up, but the plucker is allowed to run for 15 seconds, and it's shut off, coming to rest in 8 seconds. So the first thing, sketch a graph of the angular velocity against a time. So use a straight edge when you do this, but right, we're going to be graphing the angular velocity, remember that's the Greek letter omega, against time. It doesn't really say unit-wise here, but I would really like you to do this in radian per second. When I read you the homework, I think what I'll do is I'll go ahead and change that. So start by converting this 300 revolution per minute to radian per second. Now keep in mind this thing starts from rest. Right, then 2 seconds later, you know the angular velocity. Then it's just allowed to run for another 15 seconds. And the intention here is at a constant angular velocity. And then it's shut off, coming to rest in 8 seconds. So make sure your graph, when you sketch it, matches those conditions. Okay, so part B, the acceleration of the plucker at 1 second. So, and this is referring to the angular acceleration. And your angular acceleration is changed, oops. For some reason my pen quit. did some funny things there. Let me rewrite this. So your angular acceleration is the rate that your angular velocity changes. So it's equal to a change in angular velocity over change in time. And ask yourself, how does this relate to your graph? Right? What are we actually looking for on the graph? And I'll give you a hint, starts with an S. So that should be enough to answer that question. Moving on. The acceleration at 10 seconds, same type of question as B, basically the same thing. And D, virtually the same question, right? Question E, how many times did the plucker go around during the entire time frame? Well, remember, angular velocity is change in theta over change in time when you calculate it. And you can rearrange that. Our change in theta is equal to our angular velocity times time. And ask yourself, on my graph, going back to part A, what is this? And that should get you through that. All right, moving along. Oops, come on, scroll. 19, helicopter blade. So the pilot turns on the engine, accelerating the top rotor from rest to 400 RPM. So we're talking about this thing right here in the picture. Taking 12 seconds for the rotor to reach full speed. The rotor has a 16-meter diameter. Keep in mind that's this. The angular acceleration of the rotor. Well, basically you just have to know, how is that calculated? Your angular acceleration is change in angular velocity over change in time. Start by writing that out. Now, I like these in standard units, so I want this in radian per second per second. So I probably would start by converting this 400 revolution per minute to radian per second. And then you'll have your change in angular velocity, and the change in time is given in the problem. Right, part B, how many radians does, oops, I need to get an S in there, does the rotor rotate while accelerating? So it's asking for the change in theta. And remember, angular velocity is equal to change in theta over change in time. So our change in theta is equal to, whoops, our angular velocity. Oops, my computer's not, oh shit. Whoops, sorry about that. Oh, shoot. My computer just turned off for some reason. But anyway, our angular velocity is, what's going on here? My computer's not functioning, but hopefully this is still recording. Our angular velocity times time gives the change in theta, and ask yourself how that relates to your graph, okay? You can use your graph to solve this, and that's probably enough. I'm going to call this video done here as I'm having some technical issues. I hope that this helps. Have a great day. Come on.